In today's video, let's take a look at acid-base equilibrium by figuring out how to use an icebox to find the pH of a weak acid. So this question says calculate the pH of a 0.66 moles per liter solution of C5H11COOH, and the Ka value for this weak acid is also given to me here as well. Alright, so in this question I need to find the pH, so automatically I need my pH formula. We know that pH equals the negative log of the concentration of H3O+. H3O+ is your hydronium ion. So I need to know that that's actually not given to me directly in the question. All I know is that I start this solution with a 0.66 moles per liter solution of this acid. Now in this question, we're going to omit the concentration of water because it's a constant, so we don't actually put that in our equilibrium problems for weak acids and bases. And if I go to the product side, my hydronium initially in my icebox, so I stands for initial, I have 0 moles per liter. And same thing for this conjugate base, we have 0 moles per liter of it. Remember that in all equilibrium problems, products always start at 0, right? Because you haven't actually done anything yet in the reaction, so you don't have any to begin with. Okay, what about underneath change? So this is initial. Change is always going to be, again, very similar, where reactants will always decrease by their mole ratio. Now, this problem, it's a 1-to-1 to 1-to-1 mole ratio because all I really did, it's a Bronsted-Lowry equation. So all we did is we took this hydrogen ion and we moved it to the water. So that doesn't change the mole ratio or change your atom balance in anything in this question. That's how I got the hydronium and the conjugate base as my products. Okay, the products will always increase because they're always going to get formed as the reaction proceeds. So we're going to say plus X. So they change by 1X or their mole ratio. So at equilibrium, I'm going to have a value of X of hydronium. Remember, this is what I'm trying to solve. I want to know how much hydronium I have so I can plug it into my pH formula. And then I'll also have the same amount of my conjugate base. Okay, if we go to the acid on the left, I'm actually going to use a little bit of a shortcut. We're going to use approximation. So I'm going to say approximation here, where we're going to assume that X equals 0 on the left side. So at equilibrium, if X equals 0, then I'm going to have the same amount of reactant. I'm going to still have 0.66 moles per liter, approximately. So why am I doing that? It's because I have over here a weak acid. So the weak acid, the Ka value is a very small number. It's 1.3 times 10 to the negative 5. The definition of a weak acid is that it barely dissociated. So usually weak acids, they dissociate, which we can also calculate, by the way, but we'll save that for another video. They dissociate by less than 1%. So that means that like this reactant, it barely changed. So this is a very fair assumption I can make that it barely changed. And the amount of product I get on the right side will also be a very small amount. So I'm going to do that to simplify my math. And so, okay, with all that being said, I need to calculate how much hydronium do I have. So we're going to use our equilibrium expression, Ka equals the concentration of products, so hydronium, and C5H11COO-, that's my conjugate base. So again, we have to raise it to their mole ratio, but again, it's 1-to-1. So concentration of products divided by concentration of reactants. Now again, we're going to omit the water, so the reactant is C5H11COOH. So let's plug values into our equilibrium expression. So Ka, that's again given to me up here, it's 1.3 times 10 to the minus 5. It's unitless. That equals hydronium, which is X, the conjugate base, which is also X, divided by the reactants concentration, which remember we approximated, so it's 0.66 m or moles per liter. Okay, so let's actually clean up our expression here so that we can solve for X easily. So we're going to say that X squared, so X times X is X squared, that equals 1.3 times 10 to the negative 5 times 0.66 moles per liter. We're going to multiply that out, and then we're going to have to square root both sides of the equation. So I'm going to just do that in one step. So my X value will equal 2.9 times 10 to the power of negative 3 moles per liter. Okay, so remember, this is my X value. That represents my hydronium value at equilibrium as well as my conjugate base at equilibrium. I don't actually need the conjugate base for this question, but it will represent both. So X will also equal hydronium. Okay, hydronium at equilibrium will also equal this. Okay, so with that being said, now I can calculate the pH. So pH equals the negative log of hydronium's concentration. Because it's a weak acid, this is the concentration at equilibrium. So pH will equal negative log of 2.9 times 10 to the power of negative 3 moles per liter. And that will give me a pH value of 2.54. Okay, so that is the pH of a 0.66 moles per liter solution of this weak acid. The pH value will be 2.54, and that's how we solve a weak acid pH problem. If you want to see another example of acid-base equilibrium or any other type of problem, please let me know in the comments, and thank you very much for watching today. Thanks.